This last video is on a type of graph called a tree. It's a little bit different than what we've been doing before, but these have the greatest business applications of them all. Let me start with a definition. A tree is a connected graph with no circuits. And you'll see how the tree structure starts to unfold when I try to make my graphs. So let me start here. We got to start somewhere, and we'll put some branches or some edges coming off of something. Now, since it contains no circuits, I can't do this kind of business like this. I can't do anything like that, so I have to take that out. If I want to have another edge, it must come out something like this, or they could do this. This is fine, or this is fine. All of these are fine so long as I don't at any point in time create some sort of a circuit. So that's why these graphs look tree-like in many ways. And I can go on and on. Basically, they look something like this. You most probably have seen this when we did factor tree. We didn't do factor trees, but you've probably seen factor trees. When we flip coins and things like that, I think I did pictures representing those situations. So all these kind of graphs here are trees. Now some things that you want to note. Every edge is a bridge. If there are n vertices, then there are n minus 1 edges. So if you look at any of these here, I'm going to pick the simple one since I can count real fast. We have 1, 2, 3, 4 vertices, but only 3 edges. So basically you can see that we're stuck with graphs like this. If once I can't even do like this kind of a thing, like a double edge or anything like that, because it will create a circuit. There is only one path from any one vertex to any other vertex. So if we come back here, say I wanted to get from this vertex all the way out here, all the way to this vertex over here. When I go to get there, look, I'll travel a little bit here. I'll travel here. I have nowhere else to go except there. Here. Now, when I get to this vertex here, I have a choice. I can either go to the right or stay straight. If I go to the right, I'm going to dead end. So I kind of have to stay straight. I don't have a choice right here. Stop. Here, I once again have a choice to get to my desired vertex or to branch off. If I branch off to the right, I'll hit a dead end and I'll never get to my vertex. So you can see there's really only one way to go from that one vertex to the one that I wanted. I don't know. I never really put these in videos. The applications for this, there's more applications for this than I can possibly list. But wiring is certainly the first thing. Any kind of wiring around houses and things like that may use trees in some shape or form. I have seen trees used in a business atmosphere when I have been studying Gantt charts. You may have seen those when they talk about trying to allocate resources, being humans that work there. They don't want to overwhelm their resources, so trees come in very handy in keeping track of all that. And there's more things. You'll see as I do more examples, you'll see the applications are stunning. Now, what's useful here is many times we may have some sort of a wiring or some sort of a graph, and we may not want all of the graph, but we may still want some of it, a subgraph. Every connected graph contains at least one tree. So let's see an example for this. Let's start with a simple graph here. I'll pick a complete graph on 4 vertices. So I have A, B, C, D. And so there's a variety of trees that I could pick here. For example, starting at B, I could do something like this. So there's an example of a tree that's in there. I could have started a vertex at A. By the way, that counts as a tree right there. But usually you'll be looking for more complicated trees than this. In fact, I would like trees that involve all of the vertices, and that's called a spanning tree. So all of these examples that I showed in the previous example are spanning trees because they contain all the vertices. That's typically what you're going to want to do. If we look at the original picture, I took away some edges so that I arrived at my trees. And that's really, that process of thinning out or taking out some of the edges is a simplification process. It's making it usually more efficient. All right, what I have here is a graph connected and all that kind of stuff. What I want to do is come up with a spanning tree, but not just any spanning tree. I want what's called a minimal spanning tree. I want to try to come up with a spanning tree that has all of the vertices, but for the cheapest cost. I have moved the graph over so that I have space. Now what you want to do is try to reproduce the vertices as easily as as closely as possible. Alright, so I think I have all my vertices. A, B, C, D, E, F, G, H, and I think that's all of them. Now it's rather simple. To choose your minimal spanning tree, start with the lowest cost vertex that you can find anywhere on the graph. From what I see, it looks like 2.3 is going to be my cheapest edge to use, so I'm going to connect A to B. And I'll put 2.3. Now that I got that, I'm going to scan. Look, I missed one. Right here, this 2.1, that's even cheaper. Well, luckily, it didn't connect either A or B, so I'll go ahead and connect those. And I've got my 2.1. Got to be careful. It's easy to lose track of these things when you're looking at a graph. It's much better if I had the edge weights, they call them, these numbers that are attached to them. It's better if I had these edge weights listed in an Excel file, and then I could just sort them and take a look at the lowest and work that way. But for this, I'm sort of stuck looking at this and trying to decide what's cheapest. So let's take a look. From G to F is 2.5. That's pretty cheap. Let's see what's next. 2.7 I think is the cheapest one next. That connects C to H. And notice there's where those edges appear to intersect, there's no vertex there, so we're still in tree mode. Alright, what is next on our vertices? Do I have a 2.9? It was going that way, but I don't see one, so I think I'm going to take this 3.1 that goes from D to E. Now whenever you get to a tree, well, I should look at it this way. Whenever all the edges or the vertices are connected, you're done. As soon as you get to a connected graph, you're finished. So let's see what we have next. After 3.1, I see a 4. A 4 will connect B to C, so I'm going to take that unless there's another 3. I do not see it, so I'm going to take this 4.0 that connects B to C. And now I've got almost everything connected. All I need is something to touch that F or that G, and I'm done. So, oh, let me put my 2.7 here. Let's see what's next. After 4.0, the cheapest thing I see next is, I think, this 4.5. But if I try to do this here, I will have made myself a circuit, and we don't want that. So let's take it out. I'm not going to take that 4.5. So what comes next? 4.6 right here. I think that'll fit the bill, because once I make this connection here onto a 4.6, my graph is now fully connected, and I think I have everything I need. Alright, so now what we want to do is calculate what's called the total weight of the graph. That means we're going to add up all of these edge numbers, and I need to put some in, I just realized, because I forgot some. So we'll put up the total weight. And we simply add up the vertices. I'm sorry, the edges. Now, before I add these up, I do want to make a count of my vertices. So let's go ahead and do that. I have there's 1, 2, 3, 4, 5, 6, 7, 8. That means that I should have 7 edges. So let's check that out. 1, 2, 3, 4, 5, 6, 7. Excellent. Now I'm ready to add them all up and find out this total weight. My total weight is 21.3. So what we found here is called a minimal spanning tree. Now one can easily see where something like this would be useful to minimize, especially if they were wiring. You of course would want to minimize the amount of wire that you use to wire up a house. So that's a great example of where you would apply a minimal situation. Sometimes, though, we might want maximal trees, and that's where we look for the maximum of all the vertices each time. So I'm going to redo this, and I want to find So let me go ahead and pull the picture back up and do the same thing, except now we're going to keep and pay attention to our maximums. Alright, I've laid down my vertices. Now, this time, let's look for the most expensive edges. Now, this might be useful if these edges represented the amount of, say, water that is flowing through a pipe. Then the larger number may mean larger diameter pipes, and it may be more useful to go big than small in this situation. So anyways, let me look for the most expensive first edge I can find, and I believe it is this 9.5 here that connects B and D. So don't forget to put my labeling as I go. Alright, then I'm working my way backwards from that. I have a couple of choices. I have 2 choices for 9.1. So I may switch the choice later if I find it to be more useful and better for a maximal tree. So let me go ahead and take the one that I just used to connect E and F. I'm going to keep the other one circled. Well, actually, no. I wasn't even thinking. You don't have to only use that. I could branch E off and use both of them. So I was a bit short-sighted there. So I got those. Now let's find the next highest one after that. I see an 8.1 connects A, this one right here, connects A to F. So let me go ahead and put it. Got it. Now let me move on to the next most expensive edge, and it looks like the C to E. There's an edge that connects C to E that has an 8. So let me do that. Now for this, what I recommend is to take, I'm going to erase this for a minute, that 8.1 that I had, it's best to put it up here and then make your connection and try to keep it away from other numbers, because it'll be hard to keep track of them if you keep them too clustered. Alright, so I've got that. Now, let's see what we have next. I think I've got a 7.5 connecting H to G. 7.5, good. And now I somehow need one more connection to do what I need. So let's see. The next highest one I see is 6.4. Let's take a look at that one. If I try to do 6.4, this connection here, I will have created a circuit. So don't do it. It looks like I got a 6.1 connects A to D, and that'll do it right there. This guy right here, 6.1 will connect A to D. And then, like I said before, I'll take this 9.5 and I'll move it to out here. So this is our maximal spanning tree. Let me go ahead and get its total weight. So you get the gist of how this is going to work. I'm going to do one more example. This is not a really hard section, but it is time consuming sometimes. It depends on the graph you're handed. Alright, this example I pulled right out of the textbook. Now this is interesting. In this problem, the edges have been used to determine how many houses are the ones that give out candy on Halloween. So what this person's doing, they're trying to maximize the amount of candy they have for Halloween. So they've made a table of all the roads nearby and how much candy is available on those roads. If we see, we have a total of 1, 2, 3, 4, 5, 6 vertices. And luckily, Mike, the author of this problem, has decided to use different letters for each of the names. That way I can just stick with the letters. So I think the best idea normally when you're making a graph and you don't know anything is to try to make it in something of a circular fashion. So, and I'll just use first letters for each of these things. And you know what I'm going to do? I think I'm going to spread it out a little bit farther too. We'll see how that does for us. Now the first thing I'm going to look at is home to Noel. So the H to N is a 14. Mark it off. Then H to T is a 23. And then H to Vanille, Vanille is 15. So H to V is 15. And then H to Aron is 33. Well, that's a good road. And then H to L is 13. So I've got all those connections made. Now the beautiful thing with this is once I've done H, I can mark these all off. And now I'm on Noel being connected to things. So Noel can be connected first to Titus at 21. And then Noel to Vanille at a 22. And then Noel to Aron at a 30. And then finally Noel to Lightning has a 19. Moving on. Now Titus will be connected to three different things. Titus will be connected to Vanille at a 16. Titus will be connected to Aron at an 18. And then Titus will be connected to Lightning at a 27. So it's getting kind of hairy in here. I might just go and do something like this. All right, so that was, now vanilla is connected to Ron at a 22, B to A 22. And then V to L is at a 9. So I have to slide that in here too. Got it? Ron to lightning is a 12. And I've used them all up. Now, I want to maximize this time, so I want a maximal spanning tree. So conceivably, what I'll just do is keep the vertices in there. I mean, just start taking out the cheap ones, or I could keep the expensive ones. It depends. What I think we should have done in the whole problem was probably not draw the picture first. See, if you're given the picture first, then you're kind of stuck with it. I was given the data first, and that's really what I want. So what I'm going to do, even though I have drawn over it, is I'm going to go back and copy it and put it into Excel. All right, so I've got it in Excel. Now what I'm going to do is this. I'm going to copy this. You'll notice on either side of the diagonal, they have the same numbers. So I'm just going to copy down these numbers from here and here. There's an automated way to do it, I'm sure, that's much easier, but this is a small graph, so I don't have to do much work. All right, so I've got my data. Now what I'm going to do is highlight all of it. And up here, it's got data. And I am looking for sort. Right here we go. You can do it decreasing. And I'm not exactly sure why I put the 14 first, but that's not that bad of a deal to me. Remember, what we have here are 1, 2, 3, 4, 5, 6 vertices. That means we're going to have 5 edges. We're talking about candy. So we want the most candy. That means I want my 5 biggest numbers. That will be these guys down here. So we're going to see what those connect. First, let me see that 33. That 33 was a connection between A and H. So let me come back and make a drawing of just the vertices this time. And now that first one, 33, connected Ron to home. So I'll go ahead and put it in. Now let's see what our next biggest number was. And that was a 30. So what did the 30 connect? That connected A to N. So A to N gets connected with a 30. Now my next biggest edge was 27. 27 connected T to L. So L and T are connected by a 27. So far I have not created a circuit, so I'm good. I would like one more connection though to finish this off. Let's see what the next number gives us. 23. Actually I need 2 more connections. 23. Where's that connected? And where's that number? 23. H and T is connected with a 23. So I'll go around here. Got it. And I forgot about this V. So let's see how I can involve that last one. A 22. Let's take, I got 2 22, so I have my choice here. Oh, there's V. V is connected to A with a 22, so let's take a look at that. If I connect V to A with a 22, I will not create a circuit. And there we go. There's my maximal spanning tree. And let's get the total weight. That is not a bad haul for a Halloween night.